And our last problem, a moving rod in a magnetic field. A conducting rod of length 0.45 meters, that's this right here, makes contact with two conducting parallel rails. The rails are connected by a 2.5 ohm resistor. A constant force F moves the rod at a constant speed of 4.2 meters per second to the right. And you might say, how can that happen, right? A constant force, you should have acceleration. Well, there's going to be a force in this direction due to the changing magnetic field. The apparatus is in a uniform magnetic field of 1.8 Tesla that points out of the page. A. Calculate the induced EMF in the rod. B. Find the direction of the induced current in the resistor. C. Calculate the magnitude of the induced current in the resistor. D. Calculate the power dissipated in the resistor during the time when the rod moves in the field. And finally, E. Calculate the external force necessary to move the rod at a constant speed through the magnetic field. We have our givens at the top. And to calculate the induced EMF, we use our motional EMF equation, BLV, substitute in the givens, magnetic field, length of the rod, and velocity, and we get 3.4 volts. The original magnetic flux, black, increases. Now, why is it increasing? Well, the rod is covering a bigger area, so it has more flux. The area goes up. Therefore, the induced field will be in the opposite direction, so that will be into the page. Step 2, apply the right-hand grip rule for the induced field. So look at the left side of this where the resistor is. Curl your 4 fingers around the wire of the right hand into the page for the induced magnetic field. Your thumb should be pointing up, so that tells you the current is in the clockwise direction. But clockwise isn't the right answer. They asked you for the direction through the resistor, so that would be up. They might have asked you for the direction of the current through the rod, and that would have been down. Calculate the magnitude of the induced current in the resistor. Ohm's Law. I is equal to V over R, or EMF over R. We have our 3.4 volts that we calculated. The resistor is 2.5 ohms, so we get a current of 1.4 amps. Now we want the power dissipated in the resistor during the time when the rod moves in the field. We just use the power equation, I times EMF, or I times voltage, substitute in the current and the voltage, and we get 4.8 watts. Calculate the external force necessary to move the rod at constant speed through the magnetic field. We alluded to that when we set the question up. Okay, we need to find this external force. And you're generating a force in this direction due to the change in flux, due to the current going through that circuit. And that's in the left direction, pointing to the left. So to move at a constant speed, we need those two forces to balance out. So we use our motional EMF equation, where the external force has to equal the magnetic force that was generated by moving this rod over the rails. And that's just ILB. So we put in the current, we put in the length of the rod and the magnetic field, and we get an external force of 1.1 Newton.